Hello everyone. I would like to talk about the solution of the first midterm. Okay, I'm going to talk about it step by step, and after I finish, I'll talk about the how to uh, give partial credits for each problem. Okay, let's get it started. Okay, so this is a math 12 midterm number 1 solutions. Okay, so this is problem number 1. Okay, number 1 we have this. Well, we ask you to give a example, okay, of a function satisfy the given conditions. Okay, well, basically we have a four. Let me see. We have four conditions. Let me see. Because we have, say, let me list the condition. First of all, limit when x approaches -3, and then fx goes to -infinity. That's the first condition. Second condition is limit when x goes to -infinity, fx goes to +2. Okay. Third condition, f of 0 equal to 0. And fourth condition, f is odd. Okay. We ask you give an example by draw graph. So here, let's see. Suppose this is the x-axis, and here this is a y-axis. Let me see, y-axis. Okay, so this is a y, this is a x. So first of all, let's look at it. X goes to -3. 1, 2, 3. Okay, function goes to -infinity. Here doesn't say which side, so that means both sides. Okay, so first of all, we draw this is a so this is a x equal to -3. Function goes to -infinity. Okay, and then fx goes to 0. Fx 0 equal to 0. So that's like this. Now between 0 and -3, there's no condition. So we can just draw the curve like that. Okay? Remember, this is just an example. If you want to draw different curve, satisfy the condition, that's fine. Okay? Now, here we say, suppose this is 1, 2. And then function goes to 2 when x goes to -infinity. So this is y equal to 2. Okay, so that means we have, well, the simplest curve maybe we draw is like this. Okay, so this says still goes to -infinity. Okay, and then here goes to 2. So it's like that. Now, because the function is an odd function symmetric about the origin. So here's a 1, 2, 3. Okay, symmetric about origin. So when x goes to -3, function goes to -infinity. Then when x goes to +3, say x equal to +3, function should go to +infinity. Okay. So this is symmetric about origin, right? So we have that. Okay, and then when x goes to +infinity, function should go to -2. Okay, because it's a symmetric about origin. The symmetric about origin, that means when you draw a line across the origin and then intersect the curve at the point, at these 2 points, and then you have the same distance to the origin and to the point on the curve. So here we have something. Yeah, I think I need to draw it carefully. Okay. So this is okay. Yeah, I think this curve is not very good. And let me do a better picture. Okay. Well, you get an idea. Okay, that's good enough. That's good enough. So this is a y equal to -2. Okay, so that's well, we said that this is one example. Okay, so it's we draw as simple as possible, satisfy those 4 conditions. Okay. Well, let me just maybe we just do it. Put it the partial credits. I will say each straight line. Say here is a 1 point, and then 1 point, and then 1 point, and then 1 point. Right? And then, well, I will say here, because this is both sides, both direction, I will say 3 points. And then here's 3 points. I will say that. And then here, let's say here's a 2 points. And then here's a 2 points. Okay, total is 16 points. We have 6, 10, 14 now. Well, function passed through the origin. How about I put it 2 points here? Okay, so that means this is a 16 points. Okay, so that's problem number 1. Now let's see problem number 2. Okay, part A, we ask you to simplify the function. So the function is fx equal to x plus 1 over absolute value of x plus 1. We ask you to simplify. Now, of course, this simplify, you just use the definition of absolute value. Well, when x plus 1 is a positive, absolute value is itself. Okay, so that means when x is well, let's consider less than -1. Then x plus 1 is a negative. Then absolute value is equal to the opposite. So that means x plus 1 taking absolute value equal to negative x plus 1, because x plus 1 is negative, negative, positive. Okay, so x plus 1 over negative x plus 1, this is a -1. Okay, now when x is greater than greater than -1, x plus 1 is a positive. The absolute value doesn't change. If you get rid of absolute value, still x plus 1. So x plus 1 over x plus 1 is 1. And then, well, we say x equal to -1, equal to -1. The function is undefined. Let me use the UD, undefined. Okay, So that's 3 parts. Okay, so when we draw the graph, okay, so the graph looks like this. Okay, x-axis, y-axis. Now, suppose here is a -1. Okay, now here is +1. Here is a -1. Well, not defined. We put a circle here, and then this is a y equal to 1, and then here we say this is y equal to -1. Y equal to -1. Okay, notice we both part we use a circle. So at x equal to -1, you don't have a function value. So that's a circle. So that's like that. Okay, that's part A. Now part B asks you, does the limit exist? And then you need to say the reason. Okay, we say the limit exists at a point if the left side limit and right side limit both exist and equal to each other. Now you look at it when x goes to -1 from left hand side, this is equal to -1. And then limit when x approach to -1 from right hand side, fx equal to +1. Then they're not equal to each other. Not equal to each other, so this implies limit x approach to -1, fx. The limit does not exist. Okay, so this is a problem number 2. Okay, so well, this is a 12 points. I would say here is a 3 points, and the graph is a 3 points. And then I will say here's a 2 points, 2 points, and then, well, here is a 2 points. So this is a 12 points. So that's problem number 2. Okay. Now problem number 3. Let me see. Okay. Problem number 3. Problem number 3, we say, ask you find a limit. So here is a limit. X approaches 2, and then x to the 2 over 4, and then x times x minus 2. So like this one. Well, we said this one, since we cannot plug the value because the denominator equal to 0, numerator equal to 0, so we have to do some algebra. So x approach to 2, and then, well, we do a simple algebra change. It's a factor of the numerator, x plus 2, x minus 2. Denominator still x times x minus 2. Okay? Then we can cancel this x minus 2. So this is equal to limit x approach to 2, x plus 2 over x. Now this time, because function is defined at 2, this is a new function, okay? So here we just plug in 2. 4 over 2 is 2. So it's like that, okay? So, well, I would say this is the 5 points. I would say this is a 5 points, this important step. And then here is, well, the rest of it is 3 points because this is the 8 points. Okay, number 4. Okay, number 4. Number 4, we have two parts. Part A, we have fx equal to x times cubic root of 1 minus x squared. And then we ask you to find the derivative. So here we say f prime x is equal to, so we use a product rule. Derivative of first function times second function. Okay. Plus first function times derivative second function. Well, this is take a cubic root is a raised to power 1/3. So 1/3 move down. 1 minus x squared to negative 2/3. So 1/3 minus 1 is negative 2/3. And then times negative 2x. So this is using chain rule. We said that do not simplify. So we just keep it like that. Part B. Part B, we have y equal to x to the 4th plus 1 over x. Okay. Now we ask you to find the third derivative. So we have to find first derivative. First derivative. So it's a 4x third minus x to negative 2. Okay, 1 over x is the x to negative 1. And then second derivative. Second derivative, so this is equal to, say, 12x squared plus 2x to negative 3. And then the third derivative. Third derivative. So this is a 24x minus 6x to negative 4. So it's like that. Okay, so that's what we ask you to find. So here, well, if I give a partial credits, well, this is 7 points each. I would say here is 2 points. And then here is 2 points. Here is 3 points. That's 7 points. And then this one, I would say, well, your start is very important. So 3 points, and then 2 points, and 2 points. Okay, so this is 14 points. Okay, so that's problem number 4. Okay, now problem number 5. Problem number 5, we have fx equal to, say, negative x to the 3rd plus 3x squared minus 4. Okay, part A, we ask you to find the domain. Now, domain D is equal to negative infinity to positive infinity. Okay, then we say y-intercept, because it's easy to calculate it. Y-intercept, when you let x equal to 0, y equal to negative 4. Now, x-intercept, well, we need to think about it a little bit. Okay, so here, let's put it here, x-intercept. X-intercept, because of the third degree equation, so the usually when we do that, we first observe. Okay, you try some simple numbers. Okay, so for example, 1 is not, because 1 plug in, you have negative 1 plus 3 minus 4 is a negative 2. But if you think about negative 1, when you put a negative 1 in, okay, negative 1 in, so here you are going to see when x equal to negative 1, x to the 3rd is a negative 1, negative positive 1. And the negative 1 squared is a positive 1, so positive 1 plus 3 minus 4 is equal to 0. So it's a negative 1, 0. Now once you find a 0, and then the second one is easy to find, you can use f divided by x plus 1, change to a second degree equation, use a quadratic formula. That's one way to do it. Another way, you try number again, where you try the -1, +1, and then how about we try +2, -2? You try +2, 2 to the third is 8. So you have a -8, and the middle one is 3 times 4 is 12. So -8 plus 12 minus 4 is equal to 0. Okay, so in that way you can try, you try that. And then, well, you say, I forgot how to check the rational zero. How about you should just do division? So that's one way to get it, that one. So for example, I already tried here. I'm going to write here, and then let's verify that. So here is a 2, 0. Okay, so you see, you try x plus 1 as a factor. So negative x to the third plus 3x squared minus 4. So this is equal to negative x squared. So it's a negative x third. And then minus x to the 2. So when you do subtraction, so you're going to have 4x squared minus 4. Of course, this is equal to positive 4x. So 4x squared positive 4x. Then when you do subtraction, negative 4x, negative 4, right? Then the quotient is a negative 1. So it's a negative 4, sorry, negative 4. Negative 4x, negative 4. Then that's equal to that. Now, this means what? This means, say here, negative x to the third plus 3x squared minus 4 equal to x plus 1. And then here is negative x squared plus 4x minus 4. Now, this one, if you put a negative sign, this is a perfect square. That's equal to x minus 2 parentheses square. Okay? So those part, you can do it on scratch paper. Okay? You don't have to write all this. We just need to know what is the x-intercept. Okay, so that's part A. Part B, we say no asymptote. No asymptotes. If you want to explain more, is well, first of all, f x defined on we say in. Usually open interval we say in. Defined in negative infinity to positive infinity, which means what? Which means there's no vertical asymptote, because vertical asymptote is when x approaches finite, function goes to infinity. Secondly, limit x goes to infinity of fx, infinity, both positive infinity, negative infinity. This is not equal to constant, is going to, let's just put it infinity. Because when x goes to positive infinity, function goes to negative infinity, because the dominant term is negative x to the third. When x goes to negative infinity, function goes to positive infinity. Okay, so sometimes we don't put it positive, negative, that means we just say infinity. Okay, so this means we say, well, polynomial doesn't have a semantic asymptote. Okay, so that's the reason function doesn't have vertical, horizontal, or semantic asymptote. Okay, part C. Part C, we ask you to use a table, so you need to calculate first derivative, which is equal to, first derivative, we have negative 3x squared plus 6x. Now this one, if I put a negative 3x, then we have x minus 1, minus 2, sorry, minus 2. Now this equal to 0. We have two solutions, x equal to 0, x equal to 2, right? And then we calculate second derivative, which is equal to negative 6x plus 6. So you put is negative 6, you have x minus 1. Right? Now equal to 0 means x equal to 1. Okay? So we have those 3 points to break the whole interval into 4 subintervals. So when we draw the table, we put it like this. This is the table we talk about, and the problem example I did in the lecture. Okay, so here we say, first of all, negative infinity to 0, 0, and then 0 to 1, 1, and 1 to 2, 2, and then 2 to positive infinity. Well, our book also did some table, but I probably talk about it in the lecture. Our book, the table, they separate. First derivative, they put a table, and the second derivative, they put a table. I like to put the table together. So here we have a first derivative, second derivative, and then the function. Okay, so first derivative equal to 0 at 0 at 2. Now, when x is less than 0, then first derivative less than 0, you have negative 3x, x minus 2, 3 factors. All 3 factors are negative. So the multiply together is negative. And then between 0 and 2, you have 2 factor negative, negative 3 and the x minus 2. And then x is a positive. So that's positive, positive, positive. Okay? And when x greater than 2, you have 2 factors of positive, 1 factor is a negative, as multiplied together is a negative. Now the second derivative equal to 0 at 1. When x is less than 1, negative 6 times x minus 1 is a positive. So here is a positive, positive, positive. Okay? And then when x is greater than 1, well, negative 6 times x minus 1 is a negative. Okay? So now, on interval from negative infinity to 0, function is decreasing concave up, right? We say it's a decreasing concave up. We put it this symbol. And then from interval 0 to 1 is increasing concave up, increasing concave. From decreasing to increasing, so we said this is the local minimum. Okay? Now, from 1 to 2, function is increasing concave down. Increasing concave down. Because the first derivative is positive, is increasing. Second derivative negative is concave down. Now, from 2 to positive infinity is decreasing, because the first derivative is negative. Concave down, second derivative is negative. Then from increasing to decreasing, we have a local max. Now, at x equal to 1, on the left-hand side is a concave up, right-hand side is a concave down. Function is defined at that point. So this is inflection point. Okay? So this is what I like the table, because the table summarizes everything. You don't need to write that much to explain. Okay? And then part D. Part D, when we sketch a graph, before we sketch a graph, probably we should find several special points. Well, y-intercept, we already calculated earlier. Okay? And then at 1, okay, so when you plug in 1, yeah, I think the earlier we said is a negative 1 plus a 3 minus a 4, so negative 2. So this is equal to negative 2. And then F2, of course, is a 0. Well, maybe we should calculate one more point, F3. Point on the right-hand side, F3, F4 as you plug in 3, and then you see Negative 3 to a third plus 3 times the 3 squared. The first two terms cancel out. So that's equal to negative 4. Okay. Then we draw the graph. Okay. So draw the graph and then, so here, how about we just draw like this. Okay. And then here we say this is okay. Okay, how about we say this is a negative 1, negative 2, negative 3, negative 4. Okay, well, we have this point on the curve. And then negative 1, 0. Okay, that's the x-intercept here. We have this point. And then we have a 2, 0. So 1, 2, this point. Okay, and then we know at 1 function equal to negative 2, so it's this point. And then at 3, so this is 3, function equal to negative 4 again. Okay, now those 5 points, 1, 2, 3, 4, 5. Okay, then we say, first of all, from negative infinity to 0 is decreasing concave up. So decreasing concave up. Okay, and then so this is a negative 1, positive 1, positive 2, positive 3. So here we're going to say this is negative 4. Okay, now from 0 to 2, from 0 to 1 is increasing concave up. And then from 1 to 2 is increasing concave down. Okay? Yeah, let me do a better picture. Draw a better picture. So here is a concave down, increasing concave down. And then from 2 to infinity is a decreasing concave down. Yeah, I think I draw. Okay, so we say that's the graph. Okay, we have this is 1, negative 2, and then this is a 3, negative 4. Okay, so that's the graph. I think that okay. So here, if I give a partial credits, well, I'm going to say domain 1 point, and the y-intercept 1 point, and then x-intercept, I'm going to say, I'm going to give it 3 points because you need to spend a little time to figure out that. Now here we say this is a 3 points. You should realize there's no asymptote. And then we said here, of course, this part is contains more. So we say this is a 4 points, 4 points. Okay, and then the table, we say here, if I put it 2 points, you break an interval, and then here 2 points. And then now I'm going to say here is 2 points for this row, 2 points for the second row, and then 4 points for the third row, 4 points. Okay, and then here the 2 points. I'm going to say here this is 8 points. 8 points. Well, this graph you should not use a calculator. Okay, so I'm not sure if people use a calculator or not, but you have to label it correctly. So those points, I'm going to distribute this 8 points to those points correctness. Okay, so here we have, let me see, we have, let me see, 5, 8, 10, 18. 18, here is 4, 6, 10, 20, so 38. Okay, this is a big part, 38. Okay. Problem number 6. Okay, number 6. Number 6, we have a Q equal to d of x, demand function, is equal to square root of 300 minus x. Okay, part A, we ask you to find the elasticity. So E of x, the formula, just use formula, negative x times d prime x over dx. Okay. Well, how about I just write one row, because usually we say math, we write it vertical. This part, if you want to save some space, so we say x, you calculate derivative 1/2 300 minus x to negative half times -1. Remember chain rule. You need to calculate derivative of 300 minus x. Denominator is 300 minus x to positive half. Now you say negative, negative, positive. Okay? And then the 2 move to the denominator, the numerator move to the denominator, so we're going to have this is just equal to x over 2 times 300 minus x. That's it. So this is the elasticity function. Part B, okay, we ask you to calculate E at price of 250. Well, we just plug it in. Plug it in, so this is equal to 250 divided by 2 times 300 minus 250. 300 minus 250 is 50 times 2 is 100. So 250 divided by 100 is 2.5. 2.5 is greater than 1. And then this implies, we say, therefore, the demand is elastic. At x equal to 250. Well, which means if you increase the price, and the revenue should be decreasing. Okay. Part C, we ask you what price make the revenue the maximum. That means E of x must equal to 1. You solve this equation. So that means this is x over 2 times 300 minus x equal to 1. Now, of course, this implies x equal to, you multiply denominator both sides, so this 600 minus 2x. Now, this is easy to solve x. You move the 2x to the left-hand side, divide both sides by 3. So x equal to 200. Okay, so we say, therefore, we say at the price x equal to 200, we say the revenue is a maximum. Okay, so that's okay. Again, let's give a partial credit. So well, this part should be easy. We say this part give 4 points. Okay, and this part give 3 points, and the answer 1 point. And this is 3 points, and the answer is 1 point. Okay, so this is 12 points. Okay, so this is the solution and the grading scale, partial the credit. Okay, So, well, I hope you, when you watch it, okay, make sure you understand each step, okay? Yeah, sometimes the people ask a question, from the question, I can de decide probably the person does not watch the solution carefully. Okay, so please watch it carefully, make sure you understand every step. Okay, so, well, I haven't started grading yet. Okay, I'm going to do the, I'll try to grade as soon as possible and then try to finish as soon as possible. Okay, I'll talk to you next time. Bye bye.